In our Reactions Benzene podcast, we're going to go over 3 different types of reaction. Most important to us is going to be the halogenation reaction that we cover. So benzene typically will undergo a substitution reaction. This means we are not breaking any double bonds to add anything, whether it be a hydrogen or a halogen to that. Remember that your double bonds in a benzene ring are in resonance, so your electrons are moving freely, and therefore you have a lot of stability. So a substitution is the only reaction that they're going to go through. The reactions we're going to go through are halogenations, nitration, and sulfonation. Halogenation is our first one. It's going to require a catalyst. Typically, we'll use iron 3 chloride. So generally speaking, when we have this reaction, we're going to start with a benzene ring. Ooh, that's bad. And we are going to add to it a halogen. In this case, we'll just say it's a diatomic element in the presence of iron 3 chloride. So in this situation, I'm going to draw on here a hydrogen just to kind of emphasize what's going on. In a substitution reaction, we're going to remove a hydrogen from our benzene ring, and we're going to replace that with one of our halogens. So what's going to happen is this hydrogen is going to come off the ring, and it's going to interact with one of our halogens, and that's going to produce our side product. So we are going to have a hydrogen halide as our side product. And then the other halogen is going to attach to the carbon where the hydrogen was. So our final product will be a benzene ring with a halogen on it. All right, so let's take a look at an example of a halogenation of benzene. So our word problem tells us that benzene is going to react with chlorine gas in the presence of our catalyst iron 3 chloride. So I'm going to start by drawing our reactants. We have some terrible benzenes going on today. It's reacting with chlorine gas. Chlorine gas is a diatomic element, so I'm going to draw Cl2. And actually, let's go ahead and draw this with our CLs separate so that we can see where each of our CLs are going. And this is happening in the presence of iron 3 chloride. Okay, so just like the previous example, I'm going to draw this hydrogen there. You wouldn't typically show that on a skeletal structure, but I want to emphasize it here because we're going to remove a hydrogen and it's going to interact with one of our chlorines. So our side product is going to be the hydrogen halide, HCl, which is hydrochloric acid. The other chlorine is going to attach itself to the ring. Notice that I'm not breaking any double bonds. You're not going to break any double bonds because this is not an addition reaction. It's a substitution reaction. So my final product is going to be a benzene ring with a chlorine on it. And we would name this with benzene as our parent chain. And then we don't have to put the location of the chlorine since it's the only group on there. So I could just call this chlorobenzene. And chlorobenzene is one of the first reactions in the synthesis of DDT. A good example of the use of a chlorination of benzene reaction is in the synthesis of DDT. So looking at this image, this is a result of a chlorination of benzene. So we have 2 chlorobenzenes here. In the second step of this, we were able to synthesize DDT. So DDT is a pesticide. It has it's really good at what it does. DDT is able to kill off insect species that carry diseases such as malaria or typhus, and it's incredibly effective at doing so too. Because of its ability to control insect populations and therefore prevent the spread of disease, it's saved millions of lives each year. DDT is weakly polar and is a very stable organic compound, so it's not going to break down very easily. Because of this, it has persisted in the environment over the years, and because it is soluble in organic media, we can consider that to be soluble in nonpolar solvents or nonpolar substances. It's able to accumulate in fatty tissues of animals because that is also nonpolar. Most adults in the United States do have low concentrations of DDT in their body. We're not sure what the health consequences or effects long-term are of having certain levels of DDT in it. We do know that it does have a direct harmful effect on eggshell formation of certain predator birds. So you've heard of eagles laying eggs that have softer shells because of their accumulation of DDT, and that has caused the shells to break before they reach maturity, so there's a little bit of an issue there. Our next reaction of benzene is going to be a nitration. This is going to require an acid catalyst, so sulfuric acid in this case is going to be used, and it needs to be heated with nitric acid, which is HNO3. And what this is going to do is essentially add a nitro group to our benzene ring. So let's look at this reaction. We're going to start with a benzene ring. I am again just going to draw that hydrogen on there to emphasize where the substitution is happening. And we're going to add that to, and I'm not going to write HNO3 the way it is. I'm going to write it a little bit differently just to show us what's going on. NO2 is going to be that nitro group that we're adding, so I kind of want to show what that looks like by itself so we can see the full reaction. And again, this is happening in the presence of an acid catalyst, and we were told it was sulfuric acid, so we're going to put that over our arrow. All right, so in this reaction, we are going to substitute a hydrogen. So we have to take a hydrogen off. And in its place, we're going to put on to that carbon a nitro group. So we have this hydroxyl group that's left that's going to interact with the hydrogen that was removed, and what we wind up with as a side product is water. Okay, so our final product is a benzene ring with a nitro group on it. And we would call this nitrobenzene. All right, so nitration reactions can be really important in medicine because when we get that nitro group on a benzene, it can be readily converted into what we call an amino group on the benzene ring. There are a lot of different antibacterial drugs, specifically sulfa drugs, that are going to require an NH2 bonded to the benzene ring, for example, here. One specific drug that requires that is sulfanilamide. So that's a drug that you're looking at right here. This is one of the first antibiotics that was synthesized. It was synthesized around 1930s. We do have new sulfa drugs that are available now, but this one is the one that we started with. So sulfanilamide, before we get into how that works, let's first talk about p-aminobenzoic acid. So bacterial cells, which is what antibacteria agents work on, are able to make their own folic acid, and they do that with the help of p-aminobenzoic acid, also affectionately known as PABA. PABA is used by bacterial cells to create folic acid. Specifically, this portion of the structure is used by the bacterial cells. This is what they use. They incorporate that into the synthesis of folic acid. So that is folic acid, comes directly from PABA. When you administer a sulfanilamide drug or a sulfa drug, that is essentially your bacterial cell is going to start using this antibacterial agent in place of PABA. So it mistakes it mistakes sulfanilamide for PABA. So it tries to incorporate the sulfanilamide into its machinery for making folic acid, and it can't do this. It essentially is going to derail the bacteria's ability to make its own folic acid, and therefore the bacteria is going to die.